Hey Doug, how you doing?
Good. How are you guys?
I'm gonna have my video off because I'm zooming through the phone.
Okay.
Yeah, so
You
it's
know that?
charging.
No worries. Thank you for that. All right, I got some sweet stuff to show you guys today.
All right.
Oh my gosh. So let me get, man, that's unfortunate. What happened to all those? Where did those go? Oh, there they are. Somehow they got in the wrong location. Sample projects. So let's see. Give me one second to organize one more thing here. So anything you want to discuss about the test, I would of course be exceedingly happy to do so, because that's very important. Obviously that's kind of a one-on-one thing, but I have all of your tests saved. I graded them so long ago that I don't even remember anything about what went down with that. I remember a general sense of like, hey, cool. But as I've said before, I would abundantly invite your arguments about your scores, and if there's something you didn't make clear, and that's your fault for maybe not making it clear, but if you if you know something that I wasn't able to ascertain, or maybe I really would encourage you to argue about partial credit, because sometimes it's hard for me to tell. But your work is a lot of your work is getting really good, really readable. So good for you. Let's see. Let's start off with this. So it sounds like we're on for tomorrow, which is awesome. 11 o'clock. I actually drove past that last night. Why in the world was I over there? Oh, my daughter, we were taking a piano to her house. And that crane is all lit up at night. So anyway, you're going to love this lunch spot that I'm going to take you to. And this tower crane is killer. So can't get a better introduction to this than what we are talking about today. So let's see, where shall we start? Chapter resources. Let's go look at the Encyclopedia of Trusses. So I've mentioned 1,000 times that I draw house plans, etc. And one of the things I'm doing a lot is speccing out trusses. I'm not an engineer, so therefore I can't design the trusses. But I guess I'd like you to understand exactly what that means. Now, in My Open Math, I actually posted this Encyclopedia of Trusses. It's a PDF document that you can search it yourself online and download it. And I'm not going to go into a ton of details in it, which irritates the snot out of me because it's so dang cool. But I'd like to at least have you look at this page right here, because it's kind of awesome. So we're going to start looking at today. And again, as I said before, the cool thing about this is you don't have to learn anything new. Like, you already know this. We have to make the sum of the forces in X, Y, and the sum of the moments be 0. But the brilliance of a truss, and let's take a look at this Howe truss. And by the way, notice these names, Fink W truss. Notice that makes sense. There's a W there. And a Howe K truss. I mean, maybe those look like a K somehow. I'm not seeing a K right now, but maybe there's a K right there. But Fink and Howe, and let's see, are there any other names in here? I thought there were 3. There's one more that I can't think of, but Fink and Howe, were those are people that lived in this country. And back when bridges started, it was like time to get serious, because people invented the iron horse, the train. And now all of a sudden, if you're going to get one of those babies across a river, like, you're not just going to fall a tree and walk over it, like they would have done with a wagon train. Throw some sticks over a couple of trees and just, get the wagon across there. you're going to have to get really serious about how to build a bridge if you want to train to be able to. And so these names were last names of train engineers. And again, I would invite you for some extra credit because I haven't looked into that any more than what I just told you, to go investigate that a little bit. You know, who were these people? When did they live? And what they really did is they came up with these web designs. And so I'd like you to understand a little more about trusses and what's in your book. So take a look at this. This on the top right here, let me zoom in a little bit more. This on the top right here is called the top chord. So those are two top chords. And then there's a bottom chord. And so, of course, this is what you experience as the roof on the outside of the house. And this is what you experience as the ceiling on the inside of your house. But what you never see is what's called the web inside this, which is just a bunch of sticks. And so all together, that actually supports the weight of the roof. And it's just super brilliant. And you might notice on here too, because this is neat, there's a bunch of plates on here. I don't have time to show you all this stuff, but those plates are really cool. They're like, it's like a piece of metal that has a teeth that push through it. And so now there's all these teeth sticking out, and they lay them on both sides of the truss and just smash them in there with this huge roller. It's really cool to actually hold these together. The end result is these are engineered, and we're going to have a project about this a little bit later on. But what we want to talk about today is just kind of the forces that are acting on all these things, and like try to understand, you know, if you have, well, actually, you tell me, what actually causes all the forces? Like, notice there's no arrows pointing at this saying 9 newtons or whatever. What causes there to be force on that roof? I'd like you to brainstorm with me a little bit here. Where do the forces come from that are acting on this? The arrows that your author is always adding to your pictures. Well, look up at your ceiling right now. You don't see this wood. What do you see up there?
Sheetrock.
Sheetrock. It's got weight. So that bottom chord has weight, and then the wood itself has weight. So that bottom usually has what's called a dead load of sheetrock, because you put sheetrock up there and it's dead. It never moves. On the top, you also have dead load because you have roofing. But what do you have on the top that's live load? I think we discussed this a little bit, but what's up here that's live load that comes and goes?
Could be snow or...
Yeah, primarily snow. Rain a little bit, but primarily snow. And so where you live down here in the valley, we don't get a ton of snow. And so our live load down here in the valley is 25 pounds per square foot. That's what you load this truss with in our valley floor. But I'm drawing a house plan right now for somebody whose house is up at the top of the Siskiyous, and the snow load up there was 80 pounds per square foot. So it depends where you are. And you got to look that stuff up. And I found a website where you can actually find the answer to that question. And so that's where all these loads come from. And let me just tell you one thing quickly ahead of time. So let's say this length right here is 6 feet long. Well, as I said, that's 25 pounds per square foot. So if that's 25, if this truss was only 1 foot of the building, kind of like we did that project earlier, then there'd be 25 pounds per square foot times 6 feet. That's 150 pounds that would be on this chunk of the truss right there. Does that make sense? If the truss was only a foot, only carrying a foot of the roof. Well, perhaps you can see then that you would put one arrow right here in the middle that would be 150 pounds. Does it make sense that that would cause this joint to carry 75 of that and this joint to carry 75 of that? Like, that's where these arrows come from. So in this case, from the middle over, that might be 75 pounds, but then right over here, there's another 3 feet. So there's another 75 pounds. So in a sense, there'd be an arrow right here pointing at that joint with 150 pounds on it. And that's what loads this truss. That's where these arrows come from. So we're going to get into that, which again is beyond what's the scope of this class, but I just think it's so cool. And I want you to understand this so you can be awesome in your future classes in engineering. But let's dig into this. So as I said, that this encyclopedia of trusses. I posted at My Open Math, so you can actually pull this up yourself and kind of play around with it a little bit. And we're going to spend all week talking about trusses, which I'm exceedingly excited about. So I am going to bring up a book problem to start this with. And as we go along, I will show you more and more practical examples of this kind of stuff that's a little bit more interesting than the book. But I first want to convince you that you actually already know this. Like, this isn't actually hard. You're good right now. So I'm bringing a new node in. The node is in. I'm sharing a screen now. And ba-bam, there we go. So your first reaction to this should be, I'm not afraid of that right now, because isn't that what we've been doing? Like, you just got some structure with a bunch of arrows with weight on it. So notice they're telling us here that P1 is 3 kilonewtons and P2 is 6 kilonewtons. Again, doesn't that feel very arbitrary? Like, where the heck is that coming from? What do you got, a 3,000 Newton bird on one place and 6 on the other? But you can probably appreciate, even though this is just kind of a fake drawing, that, you know, if this was a bridge over a river, you would have trucks driving across it, right? And so maybe the wheels, maybe the axle is at C, the axle of the trailer is at C, and the axle of the engine under the front wheels is at B, and maybe the engine weighs not as much as the load. And so you could actually have a truss that would get loaded like this. So this isn't a roof truss. There's no snow on it. It's just a car driving over the bridge. Now, let's see if we can do what this says. Notice it says determine the forces in each member of the truss. Oh, that's different. Wow. How many members does that truss have? How many pieces of metal? That's what an engineer calls a member. A piece of cable, a piece of steel, something that connects a couple of joints. I see 1, 2, 3, 4, 5, 6, 7. There's 7 different bars. And what we got to do now is find them all. And can you appreciate? Of course you do. Like, you're the engineer. We got to figure out how much force is on each of one of those bars, and then choose the bar appropriate to that force. So even though that's a really simple truss, there's 7 different bars we got to find here. So this is really time consuming. So I got all kinds of cool things to show you. Now you also should look at that and go, I don't know, that's suddenly, now that you say that, man, that's confusing. There's like a lot going on there. And so what we're going to look at in this section is something called the method of joints. Which basically means, notice there's A, B, C, D, E. There's 5 joints. There's 5 of them in this drawing. It means you can look at one at a time instead of staring at that and being overwhelmed by, wait, and you watch this with me right now, like if you pulled down on this with 3 kilonewtons, then you could probably agree with me that that's going to stretch. That's going to put EB, the member EB, into tension, right? And that's an important part of this section, because notice it says list tension or compression. So this is going to tension that bar. Well, if it tensions that bar, isn't that bar hooked to this bar? So isn't AE going to also want to get longer or shorter? But then isn't it also hooked to this one? It isn't also hooked to that one. So it's like you pull on one of them and all of them are going to be going, you know, like doing something to not break, right? So it just feels like, oh my gosh, what am I going to do? This is too much going on. It's too confusing. Well, the cool thing is about the method of joints, you just look at one at a time. And so it's actually not that hard. Let me show what I mean. So let's put 3 down here and 6 down here, because those were given. And of course, those are kilonewtons, but I'm just trying to keep the drawing as simple as I can. Now, there's one thing you have to do first. First. every single time. And that is find the reactions. And I'll show you this on a real truss, maybe today, maybe on Thursday. But first, you've got to find the reactions. And in this case, what do I mean by reactions? Well, if you think of this as a free body diagram, like here's your truss here with some weight pulling down on it. What's missing from the free body diagram?
The reactions at A and D.
Yeah, like that has to be sitting on something, right? So isn't the block, the apparently stack of bricks pushing up at A and also pushing up over there at D, isn't that going to have force as well? And that's what I mean. Like those are the reactions. We got to find the reactions at A and at D over here. We got to figure those out first. Now to do that, really the cool thing about this is we're just going to kind of fill this thing in other words, we're thinking of this as solid. It's not solid. That's the beauty of a truss. Like it doesn't cost as much money. We don't have to fill that thing full of metal. We're going to treat it as solid and find those reactions. Now notice there's no horizontal forces on this particular truss because the weights are going straight down. And by the way, that's really common on a truss because gravity is causing the action. So a lot of times you have no horizontal forces. Again, you already know how to do this. So I'm just going to call this one the force at A and this one the force at D. And I'm just going to let the figure tell us that those are y coordinates only, and I'm going to throw in my 3 and my 6. How are you going to find those reactions? What do you got to do? Is it the sum of the forces in y, the sum of the forces in x, or the sum of the moments? Somebody tell us.
Probably some of the moments, because we wouldn't have enough information with just the forces and y.
That's exactly right. We know for sure that force of A plus force of D have to add up to 9, but the problem is we don't know how much each one gets. Is one 4 and one 5? Are they both 4.5? Is one of them 8 and the other one 1? And so you can write a sum of the forces in y, but you're not going to have enough information. And so it's way better to do the sum of the moments. And if we pick either A or D around which to run those moments, does it make sense that gets rid of one of the forces? So if I say I'm going to do the sum of the moments around A, then I can say, fine, the force in D times its distance, which apparently is 4 plus 4 plus 4, 12. And that's positive. That's causing counterclockwise rotation. That's positive. Minus 3, which is a distance of 4, and minus 6, which is a distance of 8. That's all got to add up to 0. And by the way, that's a great way to do this. Have them all add up equal to 0. Don't just set them equal to each other. It's just a great way to do your work. And so I like this equation because it's only got one unknown. So let's see, that's 48 plus 12 is 60. I can do that in my head. Force of D is actually 5 then. So this is a really canned book problem. Force of D comes out 5 kilonewtons. And now does it make sense I could switch to the sum of the forces in y, which I'll go ahead and write down formally, even though I don't really need to, do I? Because I know I got 9 going down. I'm going to have 9 going up. So I already know the other one is 4, but just to have it written down and to be careful, as we should do as engineers. Sum of the forces in y, I've got force of A going up, which is positive. I got 3 going down. I got 6 going down. And I've got force of D going up, and that all has to equal 0. And as we just figured out, again, this is a cool way to do this. Leave force of D in it, but then, kind of plug 5 in later. And of course, that just means the force in A is 4 kilonewtons. So you always got to do that first. We found the reactions. And just because the figure is so much nicer, I'm going to go, just for the sake of the drawing, I'm going to go throw them in over here. Now, just for your growing intuition, of course, you're not surprised that this one is 5 and this one is 4. Why are you not surprised? Well, 6 is bigger than 3. So I would have expected this one to have to work harder. This brick over here has to work harder than that one. Now, did I know it was 5 and 4? No, frankly, because of symmetry, I thought it was going to be 6 and 3. I thought this would be 6 and this would probably be 3. But it wasn't. But I'm not surprised this is bigger. If this came out 4 and this came out 5, I would go, wait a second, something's wrong. So just always be thinking as an engineer, always be looking at your work and just kind of saying, does this make sense? So really important. I wish I could sound a siren right now. That's the first thing you have to do with trusses. Fill it in. Fill it solid, as though there's no members inside, and get those reactions. Because see, now you know something that you didn't know before. So now we move on to second. So I better write the word out since I wrote the word out before. Second. Now we can move to the joints. The question is, which joint? Should I go A? Should I go E, B, C, D? Which one should I go to? And there's a right answer to that question. Super important question. Which one first? E is terrible. Why is E a terrible choice? E is the worst choice you could possibly make.
We don't know anything in E.
You know nothing. Like none of the forces are on it. Does that make sense? You know nothing about E. Don't go there. E is terrible. What about, I don't know, A? Is A good? The answer is yes. Now you need to think A is not the only good choice here. D is the same. D is the same good choice. But you got to think, am I going to write an equation with vertical forces or horizontal forces? That's the thing you got to think about. Do you agree that AE is the only member that can push back against this? Would you agree that that 4 down there makes the point A, the joint A wants to go up right now? A is being pushed on vertically by 4. Based on the free body diagram, if you push on A over here by 4, then A is going up in the air. We can't have that, right? That's our job as engineers in statics. We can't have that. That thing can't go up. So the only member that can fix it is AE. Do you agree that this member can't help with vertical because it only pushes horizontally, so it can't help? Now there's 2 members I don't know here. I don't know either one of those, the force on either one of those, but AE is the only one that's going to fix the vertical problem. Do you see what I'm saying? For that reason, would you agree I could start here as well? Notice because this is pulling down, would you agree this has to pull up? I'm trying to get each joint not to move. That's the method of joints. You just look at one joint at a time and you say, what forces do I have to assign to these members so that none of the joints move? If I can get all 5 of these joints not to move, congratulations, the bridge doesn't move. So actually I could start at A, B, C, or D here. Any of those would actually be fine. Sometimes there's less choices than that, but you got to be a little creative with this stuff. So let's start at A. And you might get organized. You might do something like this, like say, I'm going to look at A, like I'm going to get A not to move. So that's the first joint I'm going to look at. Now I'm going to write a bunch of equations and do a bunch of math. So let's see. The only thing I can really do there is say I'd like the sum of the forces in Y to be 0. and I have 4 going up. And then it's, what am I going to call that? What would you call that? Do I call it AE? Do I give it a new name, like call it 1, 2, 3, 4, 5? Like I got 7 members. Do I name them 1, 2, 3, 4, 5? I don't know. I'm going to call it AE. I don't want to relabel it, so I'm just going to call it AE, EA. I don't care which. Why is this not true right now? What's wrong with that statement?
It's only affects the Y portion of AE.
Yeah, that's pushing at an angle. So that's all that member can do. Does that make sense? Is push at an angle. But like we've been doing for a long time now, you've got to convert that to vertical. AE is not pushing vertically. So you got to multiply it by its ratio or sine of an angle or something like that. And then not only that, but isn't it down? Like it's negative, right? Isn't it pointing down? Do you see how I added that arrow? That's actually really important. Like come in and draw the arrow. Like it obviously has to point down. Otherwise, A is going to move up. It has to point down, which means that pipe is pushing outwards. And by the way, if it's pushing outwards with one, it's automatically pushing outwards with the other one, which means there's also an arrow over there. In other words, it can only either push both directions or pull both directions. By the way, just based on common sense, would you say that's compression or tension? Is AE being compressed and it's pushing back against it? Or is it being stretched out as a result of 4 pushing up on it?
That would have to be tension then.
And that's confusing about this. And by the way, I have my own way of teaching this that I think is better. And so if you read the book, you may end up either disagreeing with me or disagreeing with the book. But do you agree that these arrows have to be pushing in this direction? At least the lower one has to be pushing out. What I'm saying is that's what the pipe is doing. In other words, it's actively pushing out. If it's actively pushing out, that means it's being compressed and it's trying to fight against that compression. So arrows, in my way of thinking about this, arrows out, that's compression. So those arrows represent how the pipe is having to react, not what is happening to the pipe. If you think what's happening to the pipe, then the arrows would be pointing in. Does that make sense? But what we're saying is no, the pipe actually has to push out. I need those 2 arrows to counteract each other. So in my way of thinking, the arrows represent what the pipe is having to do, not what the pipe is having done to it. So if it's arrows out, it's under compression. So what's the modifier to get this thing to be vertical? Well, you got to pay close attention to this to get this from the dimensions. But you know, what angle is that pipe at? Isn't it a vertical of 6 meters, thanks to that number over there? But look at its horizontal. Isn't its horizontal going from here all the way to the center? So that'd be 4 plus half of 4 would be 6. So that thing is actually at a 45-degree angle. So you could say, oh, 45 degrees. I'm going to use 45 degrees. I'll say times the cosine of 45 degrees. I'm going to use the lengths and just let them do the work. So this would be the square root of 72, the hypotenuse would be. So what's the modification for vertical then in my formula? I'd be multiplying that by 6 vertically over the square root of 72. And that's it. That's the only 2 pipes that can contribute vertically. Therefore, I can say those 2 working together better be 0. Again, I would ask you, please immediately interrupt and let's have discussions. So let's see, if I solve this, I'm really adding force of AE times 6 over square root of 72 to both sides, and then I'm multiplying 4 by the square root of 72. And then I'm dividing that by 6, and so I'm getting 5 point force of AE is 5.66, I'm going to say, kilonewtons of compression. Do you understand why it's bigger? Why is it bigger than 4? You might have thought it'd be 4. Well, it's just not pushing at a very efficient angle, right? The worse angle you push at, the harder you're going to have to push. So by pushing at 5.7 kilonewtons at an angle, that's achieving 4 vertically. So think carefully here. Is A now static? Is A not moving? Have we achieved it? Landon, what do you think? Have we achieved it? Is A now static? It's okay to say you don't know if you don't, or to make a hypothesis. I think, but I'm not sure. What do you think?
Well, I'm kind of trying to divorce like the simplified model with like the other stuff that I know needs to be going on. So let me think.
We fixed the vertical problem. Would you agree with that? Now, remember what that means is if you buy a pipe that is strong enough to resist 5 point, we'll round it up to 6 kilonewtons of compression, then that means the bridge won't break. You're asking that member to do that job. And so put something in big enough that when you put that weight on it, it won't actually compress. Can you appreciate like a straw that you drink with is going to just get smashed if you put that much pressure on it? Better not put a straw in there. It's like, so I got to look this up on a chart somewhere, right? And see like, you know, okay, I'll use a 3-inch diameter. I'll use a 3x4 piece of tubing. And then I got to think how thick is the wall of that. And then I look up on a chart, like, will that compress if I put, remember, that's actually 5,660 newtons of force on it because we're talking kilonewtons. I got to look that up in a chart. I fixed the vertical problem. Unfortunately, though, do you see that that actually caused a horizontal problem that we didn't even have before? Do you see that?
Yep. Because it's not pushing straight down.
Yeah, because it's pushing at an angle. Well, I now have an arrow pushing at A that has a horizontal component, which means now A wants to push to the left. Watch my arms really quick. If I put weight on the top of my arms, isn't that going to want to make my elbows push out? I mean, that's what's happening here. In other words, this is going to try to tip over those concrete. Like I wouldn't have thought I even had to think about that because all the forces are vertical and there's like no horizontal force. And yet, because that's pushing at an angle, it's pushing it left, which means we're going to have to stop that. What's going to stop it? There's only one thing. This member pulling back to the right. You agree with that? What you see with these problems is kind of a domino effect. In other words, you start at one joint and it creates this domino effect. And so member AB is going to actually have to pull back. Remember, just like my arms, if you pull with one arm, then you're automatically pulling with the other one too, which means there's also an arrow on this side that's pulling that way as a result. Again, This is what the beam is having to do, not what is being done to the beam or the member, but what it's having to do in response. So notice that is arrows in. In other words, here's the beam sitting here and it's having to go and pull in to keep this from happening, right? Well, why is it pulling in? Because it's being tensioned, it's being stretched out. So if you have arrows in, that is tension. So that's huge. Again, I'm teaching you what I consider to be the easiest way to think about this stuff. And this is not the way the book teaches it. I can totally watch this stuff happening. Okay, well, let's go do that. So is joint A not moving? Well, not vertically, but it is moving horizontally. So we got to keep going here. So what's the sum of the forces in X? I need that to be 0. Well, how hard is that pushing left? Well, I think I'll just write it this way this time. I have that 5.66, but again, that's the angled version of that force. And I've got to modify it according to this horizontal. And again, I hope this seems familiar to you, but according to the horizontal, what horizontal component is it going to be? Well, the horizontal and vertical are equal. And by the way, now I'll go ahead and write this, but so that's going to have to be modified by 6 over the square root of 72. Now I'm going to type that in my calculator really quick. 5.66 times 6 divided by the square root of 72. That whole thing just came out 4. Look at the picture. Why did that come out 4?
Because we have like the bricks pushing up, like the force going up.
Yeah.
From the ground up.
And therefore, wouldn't that member AE have to be also pushing down with 4? So 5.66 at an angle must be 4 modified to vertical, right? And since these two numbers were identical up here, then that means the horizontal would be 4 too. So in a sense, that's not a surprise. I wouldn't necessarily notice that, but it's like, oh yeah, I guess that makes sense. So what's going to stop that? Now notice again, that's actually going left. And so I should go back here and throw a negative sign in front of this, shouldn't I? Because my arrow is pushing left. So that's actually negative. Well, according to our picture, isn't AB pulling back to the right? And notice that thing's horizontal, which means I don't even have to modify it. It's horizontal right now. I don't have to multiply it by anything. So AB is pulling back to the right. So no modification. So plus force of AB needs to be 0. So that means the force of AB is just 4 kilonewtons. And very important, tension. We've ignored the entire rest of this bridge, this truss, but now joint A is static. So we're done. We can move on to something else. Remember what that means. It just means that, well, it's static if you choose a bar, a member AB that's strong enough not to rip in half with 4,000 newtons pulling on it. Do you understand that? Could I put a piece of string there and it rips in half? Yeah, like you have to choose a bar that's capable of this. You understand the logic to that? Just assigning a force to it is not the point. It's saying this is how much force is going to be required of it in order to stay static. And so we better go choose something that can do it. Last night I moved a piano with my son-in-law and future son-in-law. Well, We invited people that can lift pianos. Does that make sense? There's pianos to be lifted. We did not invite my 1-year-old grandson. He was not invited to help. So you got to invite members to this trust that can actually do the work that we just figured out that's required of them. What joint should we move to? Now, what I want you to see is, do you see the domino effect? As a result of this member needing to pull to the right with 4 kilonewtons, does it make sense the right hand is also pulling 4 kilonewtons as well? Which means all of a sudden joint B is being pulled to the left as a result of this. Again, think about it. This makes perfect sense. If this is pushing on this, and this whole brick wants to tip over, then isn't that going to pull on this, which in turn is going to pull on this? So of course that joint is going to get pulled to the left too, as a result. That's the idea. So if that's true, then this joint better pull back. Why can we not move to location B now? Why do we not want to move to B next? Well, we can, but we can't solve the horizontal problem at B next. Do you understand that? Because this is having a horizontal effect, but this is also having a horizontal effect. So how do we know how much each one does? Well, we don't. We can't, like your next move is not to move to B and say, let's find out what the sum of the forces in X is. I can't go to the sum of the forces in X because there's 2 members that are going to stop that 4, right? This joint now wants to move left 4, and both of these members can stop that. And I don't know how much each one's going to get. But I could move to B if I did what?
Did the vertical forces.
The sum of the forces in Y, because this one is horizontal, which means it won't make a contribution. And so I could move here because only this one is going to be able to pull back against that 3. So I could move to B. Again, I don't want to go to E yet. Even though I now know something, keep in mind, I know that this is pushing with 5.66 now. That's why I like to draw the arrows this way, because what we just discovered is E is being pushed in this direction, 5.66 now. So I know one of them, but I still have 3 that I don't know. So I don't want to go to E yet. So let's move to B and do the sum of the forces in Y. And as I said before, we could have moved here in this particular problem, we could have moved there first. So I've got 3 going down. That's super easy. And then I've got the force of EB going up. So it's positive. Force of EB going up. And again, why is it going up? Because it's the only one that can. That's why it's important to come back here and draw this arrow in. Which means there's a mirror image of it coming up here. Isn't that interesting? This bar here was in compression, but this bar is actually in tension. Isn't that cool? Like you never would have thought of that. When you first looked at this, you just thought, oh, all the bars are working, but like some of them are being smashed and some are being stretched. And until you wade into the method of joints, you can't actually tell. So that's kind of cool. But again, I got to modify this, right? Well, what angle is this thing at? Well, it has a vertical of 6, but its horizontal is only 2, right? And 36 and 4 is 40. So that hypotenuse right there is the square root of 40. Whew, that's terrible. I got to do that again somehow. I'm not sure what to do with that. It's so small. I guess I'll draw an arrow. By the way, could you agree with me that if I redrew a nice, huge free body diagram at the top of my page and made it gigantic, that would be nice, wouldn't it? That'd make it a lot better. I have a free body diagram here in a sense, but it would be much better if I had redrawn this. So what modification then does that force of EB need if I want it to be vertical only? Do you agree it's 6, which is vertical, over the square root of 40? That's the proportion of it that's vertical. Again, you're more than welcome to come up with this angle right here. Do inverse tangent of 6 over 2 and come up with that angle if you want to, and use sines and cosines. But sines and cosines are ratios anyway. In other words, I'd be using the sine of this angle, which is opposite over hypotenuse. I already have the opposite on hypotenuse, so why not just write it down? So that's got to be multiplied by 6 over the square root of 40. Again, that's not new. I hope you agree with that, but I would invite you to interrupt. So that's its modifier. Those are the only two members that can contend with the vertical desire that joint B has to move. And so I can say good, and then that's equal to 0. If I solve that by adding 3 to both sides and then multiplying by the square root of 40 and then dividing by 6, I get 3.16 for force of EB. And because it was arrows out, that's tension. I'm sorry, I said it backwards. Because that was arrows in, that's tension. As before, you should not be surprised. This is a little bigger than 3, but notice it's not much bigger than 3 because that was almost pulling vertical. If it was pulling vertical, it would have been 3. If you tilt it a little bit, it'll be a hair more than 3. If you tilt it way over, it'll be a lot more. That's why this first one, although it was 4, this is tilted way over. So it had to pull way harder than 4, or push way harder than 4 to fix the problem. So this didn't have to pull near as hard because it wasn't at such a steep angle. So you should not be surprised that that's bigger than 3, but not way bigger. If you got something like 5 for that, you should say, something doesn't seem right there. Domino effect. Does it make sense that now we could move on to fix the horizontal problem? Now, this is interesting. If I look at this joint, I see this is pulling to the right and this is pulling to the left. And so I'm not really sure what BC is going to do. Do you agree with me there? I actually, for the first time, I don't know what way to draw this arrow. I'm actually not sure. Let's see. Well, maybe I am. Let's reason about this a little more. How hard was this pulling to the left? Force of AB. It was 4, right? It was 4. So who's going to win? This is pulling to the left at 4, and this is pulling, well, not very much to the right. Would you agree with that? It's not pulling very hard to the right. So can you see who's winning that tug of war based on logic? 4 is pulling way harder to the left. And so you can guess at this, and that's fine. What's going to happen if you guess wrong?
You get everything else wrong.
No, if you guess wrong, you just get a negative number.
Oh, yeah.
In other words, if I come in here and say, I think this is going to push this way, and therefore I'm going to call that negative because I just aimed it left, and then I get all done solving it, and then I get that force of AC is -2, then it's like, oh, idiot, you drew it the wrong direction. And I want you to understand that in this case, you could actually reason it out and be correct. I've got it wrong here, but many times with trusses, they're really confusing. It's just super cool how some are in tension, some are in compression, and especially when the truss gets really complicated, you often can't know. And so if you get it wrong, then you just go back and redraw the arrow. You want to work with a pencil and a good eraser, redraw the arrow so it's going the correct direction, because you need the arrow to be going the right way. Otherwise, it's going to screw up the next problem. Don't aim it left as I just did and then say its force is -2. That's going to screw you up later on. So it appears to me that this one's actually going to be pulling inward, which means the right side is also inward, which means this is under tension. I think that's my guess. It's my educated guess. Okay, so let's go back. And so basically what you're doing is taking every joint and fixing it vertically and horizontally. So let's go fix that joint horizontally. What would the sum of the forces in X be? Well, I had 4 pulling to the left. I had 3.16 that we just figured out a second ago, pulling to the right. But remember, that wasn't pulling to the right. That was pulling up at some weird angle. So what's the modifier? You tell me, Evald, you're up. What's the modifier that I have to multiply?
Times 2 over square root of 40.
Exactly. Times the horizontal component, 2 over square root of 40. You guys are on this. So cool. Times 2 over the square root of 40. Am I done? Is that all the forces? I hope not, because there's no letters there. We're done. What else is missing? Oh yeah, that one other arrow, the one that we're working on right here. This guy right here, force of BC, which I'm saying is positive, at least relative to B. Notice when I come over here to C, it's going to be negative. Because this is Newton's law. About every action, there's an equal and opposite reaction. If you pull left with one hand, you're going to have to pull right with the other. So that's positive to the right. And it's already horizontal. Awesome. That means I don't have to modify it by anything. So I can just say 4 plus force BC. And that's got to be 0. So that's cool. All I got to do is add 4 to the other side and then subtract 3.16 times 2 divided by the square root of 40. And I got a positive 3. I got 3 exactly. That's kind of weird. Force of B, I got 3 kilonewtons. And because it was arrows in, it's tension. So I was right. It was positive. So that means I guessed right. But 3, is that a coincidence? It came out exactly 3. I find myself wanting to say no. But actually, I don't know. Actually, I don't think it's obvious. It's not because this is 3, because that was vertical, right? So if this is 4 to the left and this is 3 to the right, then this one's horizontal component must have been exactly 1, I guess. But I guess we didn't know that, did we? So I don't want to play with that, but that's what must have happened.
Yeah, if you use exact square roots, you can kind of see it.
Good job.
Place, but of course, that won't always be the case.
Yeah, that just kind of was lucky here, if you will. Now, one of the things I want to point out is if this truss had been symmetrical, which is true on a real house, in a real house, does it make sense these two reactions over here are going to be equal? Because you have kind of an evenly distributed load, which is what we'll go talk about after this chapter. And like, you know, what is a snow load over the whole thing? Not just one arrow, but a whole bunch of arrows. If that was distributed evenly, does it make sense these would both be 5 and these would both be the same? Does it make sense these members over here would all have all the same answers and we're done? But in our case, it wasn't. Like, it was loaded asymmetrically. And so we actually have to keep going. We got to find them all. But notice we're making good progress. 1, 2, 3, 4. We found 4 of the 7 right now. We're doing awesome. Where should I go next? Well, C or D would work. As I said before, and this is an unusually simple truss in the sense that we could have gone to D from the very start because it's just like A was. It only has one pipe pushing on it. But let's just, we're progressing across the truss. Let's just go to C next. But we could go to C or D. So let's go to C next. Picking on somebody, Landon, do I want to do a force of X or force of Y first?
It's
okay to be wrong.
Force of Y then, I suppose.
You are correct. Why is that? Because this member has no contribution in Y because it's perfectly horizontal, which means this member here is the only one that can stop that 6 right there. Now we just figured out a second ago that this force right here is 3, right? It's pulling left 3, but would you agree this one can pull back and that one can pull back? So both of these are going to stop the 3. I don't want to do the sum of the forces in X first. And as I said, the interesting thing is I could have done this a long time ago, because even though this force is 3 right here, it's making no contribution vertically anyway, so who cares as far as the forces of Y are concerned. So that's force of EC. So let's go figure this out. So I've got 6 pulling down. So the sum of the forces in Y, I've got 6 pulling down, and I've got the force of EC pulling up. And again, notice I didn't draw that in, but I said up. But of course, if I go back and look at this picture, since 6 is pulling down, then this has to pull up, which means it's doing the same thing on the top end, which means it's in tension again. So interestingly, the two inner members, remember I told you those are called webs in the industry, the inner part of the triangle, because it's not actually solid in there, the 2 webs are under tension, but the top chords are under compression, and it appears that all the bottom chords are under tension. We'll talk about that more in a minute. Notice that member is at exactly the same angle as EB was. So the same triangle, 2, 6 in the square root of 40, that applies to the direction or the angle that one's pulling at. Do you agree with that? So its vertical component is 6 over the square root of 40. So that's my modification of it. I can't just say it's pulling vertically. I've got to say it is if you modify it by 6 over the square root of 40. And that's the only members pulling or pushing on it. So I can set that equal to 0. So if I add 6 to the other side, multiply by the square root of 40, and then divide by 6, I get 6.32. That's interesting. So force of EC is approximately 6.32 kilonewtons. And because it was arrows in, that's tension. Notice, just to stare at our answers so far, does it make sense? That's the hardest working bar of the entire bridge right now. This bar down here was only 3.16. This was only 3. This one's got to work twice as hard. It's going to have to be strong enough to lift twice the weight the other ones are. So that's interesting. Like, that's why you got to know all of these. Now that we know that, then we could actually proceed to the sum of the forces in X. I'm going to do this wrong on purpose, but I'm going to look at this time without thinking so much, and I'm just going to guess and say I think this is pushing to the left. I've just had enough practice that I know that's not true, and I'll tell you why really quick. I'll erase this, but if you have a beam right here, that's the bottom of your truss, and it's being supported on both sides like this. Is that beam, when it sags down, getting longer or shorter? If it's sagging like that, is it getting longer tension, or is it getting shorter?
Depends on which part.
Now the whole thing, basically
The whole thing.
under its own weight, even if there's no forces on it, its own weight is going to cause it to sag in this way. Do you agree with that? It's going to kind of go sag down.
Mm-hmm.
Do you agree it's getting longer then?
Yes.
And if it's getting longer, then it's being pulled on, which means it's under tension. The bottom chord of a truss is always under tension. So that's why, even though I haven't considered the forces, that's why I know that I drew that purple arrow the wrong direction. But let's just go ahead and do it anyway. And we'll see it come out negative, and then we'll fix it, okay? So let's see, we've got BC pulling left here, which I got to go look up what that was. I forgot. And then I've got this 6.32, which I got to modify. And then I got this pushing left as well. Notice in this case, that's idiotic to put the arrow in there the way I put it. Do you agree with that? Because these are both pulling left. Like, there's no way this is going to pull left too. Having said that, I'm going to change my mind, and I should never pick that answer here. That's stupid. At least last time it was a toss-up. This time it's not a toss-up. Okay, so I've got BC pulling left for the sum of the forces in X. And we said BC. Oh, I wrote force B back here, but I think that was force BC and I forgot the C. Force BC was 3, so that means that's pulling left 3. We just figured out that EC was also pulling left, that's 6.32. But to modify it, as Evold said a second ago, we've got to multiply by 2 over the square root of 40. That's pulling left. So duh, those are both pulling left. Well, then certainly this next one's going to have to be a plus sign, pulling right. Unfortunately, again, it's attached horizontally. So that's CD, remember CD, that's pulling right. And I don't even have to modify it by anything. It's very exciting. So if I add those to the other side, add 3 to the other side, add 6.32 to the other side, multiplied by 2, divided by the square root of 40, I get 4.998. That's interesting. It basically came out 5. So the force of CD came out 5 kilonewtons. And because it is, as I said before, arrows in, that's tension. So I need that in my answer. Tension. Again, I'm kind of wondering, like, wow, that's interesting. It came out 5. It just seems like, what's causing that? Okay, we have 6 of our 7 members calculated. We got them all except for one last one. So I'm going to move to, well, what joint should I move to? Does it make sense? You now know this member, this member, this member, you know all 3 of those, but just not that one. Therefore, you could move to E right now. But I find myself going, wow, there's 3 of them. I don't want to mess with that one. This one's only got 2. That one looks easier. I'm going to go to that one instead. But you could go to either one now. So you can go to E now for the first time. Well, you could have done it a second ago because we knew these a second ago. But let's go to D and let's just take care of the 5. Let's do a sum of the forces in Y. But would you also agree that because I know the left answer here, I could do the sum of the forces in X too? I could do either one in this problem. So D, I'm going to do the sum of the forces in Y. I know that I've got 5 pulling or pushing up, the reaction of the rock, 5 pushing up, and therefore in my drawing, I'm going to have this member pushing down against that. And it has the same exact right triangle that we just had a second ago, where this is 6 and this is 6 and this is the square root of 72. So its vertical component would be 6 over the square root of 72. So that's the force of ED. So force of ED is actually pulling down, pushing down, but it needs to be modified by 6 over the square root of 72. And that's it. That's the only 2 things that are vertical. Therefore, I can set that equal to 0. So if I do that, I end up with 7.07 force of ED. We have a new record, my friends, 7.07 kilonewtons. We have a new hardest working member of the truss. And because it's arrows out, it's back under compression again. So that's by far the hardest working member of the entire truss. Again, it is arrows out, so it's compression. Now I suddenly realize, hey, I'm done. But I never even went to E. Isn't that weird? I never went to E. And not only that, we never did a sum of the forces at D in the X direction. And so I'm going, uh-oh, man, I hope those are 0 because I never even touched them. You understand that? So let's check our work. I mean, we are, after all, going to build a bridge here that hundreds of people go over the top of, and we don't want anyone to die. So let's not just quit because we're lazy. So I'm going to make up a section here. Let's check our work because we're done. We found all the members. But let's make sure the sum of, let's see, at the point D, let's make sure that the sum of the forces in X is actually equal to 0. So I'm putting question mark. If I don't get the answer to this to be yes, I'm in a world of hurt. Do you understand that? Because I've been doing math for 45 minutes right now. And that just means something I did is wrong. I don't know what. I mean, hopefully it wasn't the original problem. Like if the very first one was wrong, then the domino effect means every single thing I did after it's wrong. And so, woo, I'm really hoping the answer to this is 0. Oh my God. So let's see, what do I have there? Well, I've got the force of CD, which again is pulling to the left, right? And I've got force of ED pushing to the right. So I'm hoping, since I know numbers for both of those now, I'm hoping those add up to 0. So let's see, CD was pulling to the left 5. I'm going to go ahead and write those in just because it looks kind of confused. You know, if I just write numbers here, you might not know what I mean. So we had force of CD, which was pulling to the left. And then we had the force of ED, which was pulling to the right. That's what we had. So what were those? Well, CD was 5. So it was 5 to the left. ED, we said, was 7.07. But to get its horizontal component, I have to multiply by 6 over the square root of 72. So I'm basically just sitting here really hoping, as I type that in my calculator, -5 plus 7.07 times 6 divided by the square root of 72. I'm hoping I get 0. I got -7.55. But then way out to the right, it says e to the -4. That's what my calculator said. Do you understand what that means? It means -0.000755. Means move the decimal point. Scientific notation for the decimal point's actually 4 places to the left of this. Do you understand you're not going to get 0 for this? Why aren't you going to get 0?
If you did any amount of rounding?
Yeah, we've been rounding the whole time. So you should expect to get close to 0, and I did. And so I'm breathing a huge sigh of relief right now because it means all those joints don't work, or that they don't move, they're static. And so I'm breathing a huge sigh of relief. So, but now I'm really maybe stressed because what if I go up to E, which I've never been to before? I never even went to E. I was terrified of it. And interestingly, I never had to go there. So I'm wondering, wow, will the sum of the forces in X and Y be 0 up there too? And again, if we haven't screwed up, do you see that they have to be? Because these things are all connected. They have to be. There's no way all those other joints aren't moving and then E is moving. Do you understand that? Look at the shape. They're all connected, right? They're all connected. So if A, B, C, and D don't move, and 4 and 5 are pushing, and 3 and 6 are pushing on them, then E can't move, right? C can't go down without E going down with it. It's impossible. They're connected, right? You see what I'm saying? Like, if I know I didn't screw up, I don't have to check this because it's impossible. If A, B, C, D are not moving, neither is E. But I might have screwed up, so that's why I'm checking my work. And so let's see. I'm really suffering for having, I'm gonna have to go back and forth a whole bunch here because I can't look at all this at one time. It's too small on my screen. I'm gonna try rotating it. That'll probably make it a little better. It actually did make it better. So let's see, I'm gonna do Y first. So switch to black because I'm in mourning right now. Some of the forces in Y. Let's see what we get for this. Well, we got force of AE. Notice it's positive, it's pushing up. Do you see why the arrows are so cool? Force of AE on the left is pushing up. So I'm going to call that positive since I'm talking about the forces of forces of Y. And again, just so that you can kind of look back at your notes later and learn from this, I'm going to say force of AE, which is positive. And then I've got to modify that by its vertical component, which is 6 over the square root of 72. And then I've got the next one over is actually pulling down. BE is pulling down. So it's negative minus force of BE pulling down. But its vertical component is 6 over the square root of 40. And then the next one over, EC is also pulling down. So it's also negative. EC is down, it's negative. Minus force of EC is negative. And its vertical component is also 6 over the square root of 40. And finally, got the last force on the other side, which is pushing up. It's arrows up. Do you see why I was really careful when I drew one arrow to jump to the other side of the member and draw the other arrow in immediately? Because now I'm looking up here and I know where all those are going. The arrows are either both out or both in. They're never one out and one in. That's impossible. So ED is also pushing up. So plus the force of ED, and it's modified by 6 over the square root of 72. And again, I'm hoping that this is 0 because I already found all these forces. So let's go back and write them in. What was force AE? Force of AE was 5.66. So in orange, 5.66. What was force of BE? Notice it's really important to carefully, because I'm not even looking up at the drawing. There's EB right there, 3.16. Notice I drew it backwards. It's BE and EB, 3.16. And then what's the force of EC? There it is, 6.32. And then finally ED, which I found last, which is 7.07. So basically, I'm sitting here sure hoping this whole mess is equal to 0. So I typed that whole thing in. Whew, I'm stressed. 5.66 times 6 divided by square root of 72. Again, I don't really have to check this because I already know this works, but I'm just giving you time to think. Times 6 divided by the square root of 40. I love graphing calculators because you can type the whole thing in and see it and make sure you didn't miss any numbers. Minus 6.32 times 6 divided by the square root of 40. Oh, man. Minus 6.32 times 6 divided by the square root of 40 plus 7.07 times this 6 divided by the square root of 72. And again, I'm not expecting this to be 0, but I'm hoping it's darn close. And I got 0.0079. Woo! Yeah, baby. Boom. Does it make sense? I really don't need to check anymore. I could check the sum of the forces in X too, but notice the sum of the forces in Y worked up there, which means I must not have screwed up anything before. So I'm at least a little lazy. I don't really need to check anything else. And so sweet, it worked. This is the beauty of a truss, because what a truss is saying, hey, you know, we got to lift a lot of weight here, but that's expensive to, you know, fill something solid. So could we just put like a few sticks inside there and carry the whole thing? Trusses are just utterly beautiful. Again, I want this class to ruin your life. When you go into big stores like Walmart from now on, look up. Usually you'll still see the trusses up there because they're kind of expensive to cover up. And so a lot of bigger buildings, you'll see the trusses. You won't see them in a house because they're ugly and they, you know, you got to have insulation. And so they'll put sheetrock up there and you can't see anything that's up there. But these are just beautiful. I mean, I love these, and especially like train trusses. Like there's one in Gold Hill, and the tower crane we're going to look at tomorrow, the entire thing is made of trusses like this. And every single member's got work to do. Did you notice none of those forces was 0? Every one of them had a job to do. Some of them had less of a job than others, but everyone had a job, which means what happens if you take one of them out or one of them fails? What happens? The whole thing is gone, like the whole thing falls into the river. And I wish we had time to search crane fails and bridge fails, and like go on YouTube and watch that. People have filmed stuff falling. Like it isn't just they show the rubble, like you can watch the whole thing go because one member failed for whatever reason. They bolted it in wrong, they chose the wrong pipe size, or maybe it rusted over the years and then it couldn't do its job anymore. Unbelievably cool. In one respect, we're done with this section. Like, you just have to go slow. But we need to practice this. I need to give you more complicated trusses. There's a couple of things I'm going to show you, like shortcuts. If you have a really complicated truss and you just want to know one member, you don't have to sit there for 5 hours and calculate all of them. Did you see the domino effect happening? There's this cool trick I'll show you in a little while where you can actually just skip over the whole truss and get over to where you were interested, and then you can just answer that question and get out. Unbelievable that you can do that. So I got a few kind of cool tricks. And of course, there's complicated trusses. There's some really interesting truss shapes that you've also got to contend with as well. What are your thoughts? I mean, I want to stop for a second and just give you a chance to breathe. I'd like to know, I actually would like to hear from the three of you. Do you feel good about this? Like, let's make a percentage. 100%. Yeah, I could kind of do this right now. I don't mean you wouldn't do it without mistakes, make an accidental mistake, but how do you feel about this? Is it working? What about you?
I need to do like the problem on my own, to just spend a decent hour, think about this on my own.
Yeah, well said. Nothing I'm saying doesn't make sense, but go ahead, Ben.
Oh, I was saying I feel good about this particular problem. If it was more complicated, then yeah, there might be parts I wouldn't be sure about. But
yeah, how about you, Landon?
Yeah, the process seems simple enough, but it definitely seems like it'll take a long time to work through these problems,
yeah.
especially if it gets any more complicated than this.
Mm-hmm. Let's see. Let's just talk for a few more minutes about a couple things. Let's see, do we have anything in here? We're not going to do this just yet, but we will do it soon. Would you agree this is an example of, if you will, what might be a little more terrifying? By the way, this is how modern bridges are built. So if you've seen the one in Gold Hill, usually you're actually driving through the bridge. But what do you notice about this one? Do you notice it's kind of like hanging underneath the road? Have you been to Lost Creek Lake? There's a bridge on the way to Prospect where you just drive on a road, but there's a huge superstructure underneath that thing. By the way, one of these failed, and I think the first year I taught this class, like 4 years ago, I forgot where it was like Wisconsin or someplace. And again, cars on it, and the whole thing goes into the river, and because one failed. So, go search failures of these things. But would you agree your first glance at this is like, my God, how long are we going to be here? This is going to take like 6 hours. Look how many members are on that thing. And of course, you're building a bridge that cars are going to drive over for 20 years, and millions of people are going to interact with it. So 6 hours is not that much to ask. But this particular question, because it's actually in your assignment, which is really not fair, actually says determine the force members in, well, it just lists a few of them. Do you see that? It just says find CD, JC, KJ, and DJ. Just find those, and then you can quit. And your thought should be like, how am I supposed to do that? Because I gotta, like, those are out in the middle of the bridge or something. And so how do I work my way out there without, and I'll show you that. That's kind of a cool trick, a cool shortcut. So let's see. We're kind of out of time, but I'll at least want to show you one other picture of something. So let me just show you something cool kind of going out the door. So I showed you that encyclopedia of trusses, and let me show you my next door neighbor's house that I drew. I drew this house plan. But I didn't design the trusses. And by the way, you can probably appreciate they have software that does all of this. Notice, why are you in this class right now? It's because of that right there. Registered professional engineer.
Oh, the screen share isn't up yet.
Signed. Like, that's that engineer's stamp. Now I can design a truss, like I can do the math. I just showed you that I basically understand the math of it, but I don't have the authority because I don't have the stamp. Do you see what I'm saying? This is what you're after. Like, you're going to stamp your work, which means nobody's checking on you.
I think we can see the screen, Doug.
I think one of you said that. My brain was, sorry about that. Interrupt sooner. This stamp right here that's on this set of drawings. So here's what I got from the truss company. This is 2018, as you can see. That stamp right there is the important thing. Doug, Ben, Evold, Landon can do the calculations after this class. Sorry, you don't get to design anything, because you got to be trained. You got to have liability insurance, because just because you know how to do it doesn't mean you're not going to make a mistake. And so that stamp is what you're after as an engineer. But let's just take a look at some of these trusses. I'm going to skip down to, because I looked at this before. Actually, let's not skip them all. Like, look at that guy. Isn't that crazy? That's in the middle of the house. And there's, maybe you can see the size of the cursor over here on the right. There is a lot of trusses in this house. Every one of them is a totally different design. So you thought that problem I just showed you a second ago was hard? You got to do like 50 of those just for one house. And you can probably appreciate softwares doing this in the world we live in. But I want to skip down to one really quick before I let you go that is at least understandable. Again, I skipped through all these earlier to find, there's only like one truss in this entire house that isn't weird. So notice that one's also kind of weird shaped. That's like the one that you just saw in your book a minute ago. But if I get down to D8, hope I'm remembering that right. There you are. D8. There's a nice normal truss. I showed you that one in the Encyclopedia of Trusses a minute ago. I think that was the Howe truss. I forgot. There was Howe and Fink, and I forgot which one. I think it was Howe. That's the Howe truss design. But I want to show you something interesting on this sheet before we go. And as I said, what you don't have here is arrows on it telling you 3 and 6 kilonewtons. You got nothing on it. What do you have? You have this right here. Stare at that. Loading. What do you suppose PSF stands for?
Pounds per square foot.
Pounds per square foot. I told you this before. Top chord, live load, 25 pounds per square foot. That's the snow load around here. Top chord dead load, 7. What's that? Well, that's the roofing. Isn't there stuff on a roof that doesn't move and stuff that's dead stays there, roofing? And then bottom chord live. Why is there no bottom chord live load? This is the bottom chord right here. No bottom chord live load? Well, yeah, nothing ever comes and goes on it. Doesn't snow there. Nobody hangs stuff from the ceiling that comes and goes. Unless you stored stuff in the attic, then it would have a live load. But it has a bottom chord dead load, which is 10 pounds per square foot. So can you see that it's these numbers right here that result in arrows all over that truss, at least conceptually, and then you start doing what we just did a second ago? That's the idea. I want to show you one other quick thing and then we'll shut up here. But notice the next thing down below this is reactions. So I want that word to mean something to you so that when you step into this world, like you actually know what you're talking about. Notice it says right here, 2, and then it says 1408, and then it says 6, and it says 1408. Where do you see 2 and 6 in that truss up there? Do you see how
It's on the two opposite sides. Like, yeah.
You see how they've named every joint? Here's joint 2, joint 3, joint 4, joint 5, joint 6, joint 8, joint 9, joint 10. There's 10 joints on this truss. And aren't the reactions, because a truss sits on an outside wall, aren't the reactions at 2 and at 6? Like that's where the wood is that's actually pushing up on the outside of the house. And so notice they've got calculated right here that that truss is going to put 1,408 pounds on those 2 walls. And so as an engineer or as a guy that draws house plans, I've got to make sure that underneath that is a footing underneath the house that will, keep that from sinking into the ground. And so our project at the end of this, I'm going to give you a truss like this and have you make that 1,408 calculation yourself and have you think about, if this is full of snow that weighs 25 pounds a square foot and it has 7 pounds of dead load on the top up here and 10 pounds on the bottom cord, like how would you turn that into arrows that are pointing or pulling on each of the joints? And that'll be more complicated than the problem we just had, because we're going to have an arrow here and here and here and here and here, and there'll be one down there and one down there and one down. There'll be arrows on every single joint. Fortunately, though, they'll be symmetrical. Whatever's pulling down at joint 2, joint 8 here, will be the same thing that's pulling down over here at joint 10. They'll be symmetrical. So we only have to do half this problem in the real world. Isn't that cool? Like you're close to being able to do something that makes people a lot of money that is over your head in your house right now. You're able to figure some stuff out that's really cool. So we'll get more on that later on. Anything you want to ask me before we go for the day? By the way, do you notice you don't see any angles on this truss? Right here, you're told that from here to here is 8 foot. That's 8 foot 2 and 13/16. And then you're told from here to here, that's 7 foot 9 and 3/16. And 7 foot 9 and 3/16, 8 foot 2 and 13/16. And notice the top row of numbers is cumulative. It goes 8 foot 2 and 13, and then you add 7 foot 9 and you get up to 16. So the overall width of this truss is right there. It's 32 feet wide. It's a 32 foot wide truss. And up here, you're told that the pitch of that is up 7 and over 12. So if you go up 7 and over 12, that's what the angle of this roof is. There's no degrees on this anywhere. It's all based on proportions, like the problem that we just did. So we'll kind of play around with that a little bit as time goes on. All right. So I'll see you guys tomorrow at Starbucks, where lies delicious foods. Is everybody going to make it? You 2 guys that are still here are going to be able to make it tomorrow?
Yeah.
I'm gonna do my best.
Mm-hmm. Okay, cool.
I think I should be able to make it still.
Hope you can make it. I think you'll enjoy it, and I know you'll enjoy the food. So,
All right. Thanks, Doug.
good show. See you guys.
Bye.
Yep. I have a quick question. When you draw this little the plank sitting on the 2 posts,
Yep.
and it's bending under its own weight, it's like the top part of the plank more like compressing and the bottom part of the plank stretching.
That's exactly right. So that's something we'll talk about later in this class too. But the top is under compression and the top is under tension. That's exactly right. And it's the internal structure of the beam that keeps the top from smashing together, which would actually let the beam fail, or it keeps the bottom from tearing, the fibers from tearing apart. So if the beam is not able to resist those 2 forces, top compression, bottom tension, then it will actually fail under that. So they are stretching, like the bottom is getting a little bit longer and the bottom and the top is actually compressing and getting a little bit shorter. So it's just that it's, you know, small enough. The beam is capable of lifting enough that it isn't hurting it, if you will. It's really similar to like I grab my skin and stretch it. Like it'll stretch to a certain point, but at some point, you know, it tears off. So yeah, it's cool stuff.
Pretty cool. Pretty cool. So, and you did send us the address we need to be tomorrow, right?
Yes, I did. So send me a text if there's anything I missed there. But yeah, I sent you guys everything to find it.
Is that was on the email, right?
Yep.
Okay, I need to go find it. All right. Thanks, Doug.
Thank you. Pleasure's mine. We'll see you later.
Yep. See ya.